Hi, I'm Brian Prier, tutoring high school physics. Today's topic is Snell's law. Snell's law describes the refraction of light. Refraction simply means light passing from one substance into another and then changes its angle. So let me demonstrate. Here we have light and it's striking a smooth glassy substance, in this case water. It's going to partially reflect. So you see here it is being reflected where the angle of entry is the same as the angle of exit, and partially refract, going into the water and having a different angle. We can find out the angle of its entry and exit using Snell's law, which states that the index of refraction of the first substance times the sine of theta 1, which is the entry angle, is equivalent to the index of refraction of the second substance times the sine of theta 2, which is the exit angle. The index of refraction is defined as the ratio between the speed of light and the speed in that particular substance. Light is actually somewhat slower in certain substances that are not a vacuum. However, air is so close to a vacuum we consider its index of refraction to be about 1. So let's work out this problem. We have light coming in through air with an index of refraction of 1, entry angle of 45 degrees, and it's entering water with an index of refraction of 1.33 degrees. What is its angle of exit? So let's run through Snell's law. So our n sub 1 is going to be 1, we don't need to worry about that, times the sine of our entry angle, 45 degrees, is equivalent to n2, 1.33, times the sine of our exit angle. So we do some multiplication, we do some division. This over here is going to be square root of 2 over 2 is equivalent to, this is about 4/3, that's our n2, times sine of theta 2. Sine of theta 2 is equivalent to 3 times square root of 2 over 8. We do arc sine of both sides, and we get our theta 2 of approximately 32 degrees. Now there's one other thing that can happen. If you change your angle enough and your initial index of refraction is greater than your secondary index of refraction, then this refraction won't really happen, and our theta 2 will actually be equal to 90 degrees. This means it'll simply skip along the surface of the substance instead of actually refracting. This is known as total internal reflection. So if n1 is greater than n sub 2, and, this is the tricky one, you can calculate a critical angle. If theta 1 is greater than the critical angle, then you end up with total internal reflection. You have your theta 2 being equal to 90 degrees. Now, our critical angle is defined as the arc sine of the second index of refraction divided by the first index of refraction. Alright, to recap. Snell's law describes refraction, which is the movement of light from one substance into another and changing of angle thereby. When light strikes a smooth glassy substance, it is partially reflected and partially refracted. Snell's law states that the first index of refraction of the first substance times sine of the entry angle is equivalent to the index of refraction of the second substance times the sine of the exit angle. The index of refraction is the ratio between the speed of light in a vacuum and the speed of light through that particular substance. Total internal reflection occurs where the index of refraction of the initial material is greater than the index of refraction of the second material, and the entry angle is greater than the critical angle, where the critical angle is defined as the arc sine of the index of refraction of the second material divided by the index of refraction of the first. Alright, that's all for now. Again, I'm Brian Prier. See you next time.